This question is about concluding and evaluating on some experimental data, and these are typically some of the hardest ones. Hi there, I'm just running through this, which is OCR Gateway paper, and this one is about terminal velocity, an experiment to do with terminal velocity. There's some kind of evaluative questions in here which are quite tricky, and there's also a Freebody Diagram question. Okay, so the students are investigating terminal velocity, which is the steady speed that you reach when the weight equals the air resistance when you're falling. Okay, so they dropped 100 gram mass from a height of 3 meters using 3 different shapes of parachute. The students recorded the time taken for each meter of the descent using a stopwatch. Here they are, around a square rectangular, different times. The students are not sure all of the parachutes reach terminal velocity. Explain why. Now, in this question, a lot of people who did this, they recognized that the round one has reached terminal velocity, basically the same speed, and the rectangular one has reached terminal velocity, basically the same time, but the square one had not. Okay, so this is the point that they're not sure that all of the parachutes reached terminal velocity. Some did and some didn't. So some of them have said, some of the answers I've seen, they said the speeds are still increasing, but you don't get a mark for that. Okay, or the times are not all the same, you don't get a mark for that. Your marks in this one have to start from the round and rectangular have reached terminal velocity because the time for the second and third meter is the same. Alright, but they're not sure that all of the parachutes, so what about the square one? The square one is still speeding up. The square one, the time is not the same. Most people, if they got this, then they just haven't really been particular about which parachutes were doing which job. Or indeed, they thought that because the times aren't exactly the same, that it was still speeding up for the round and the rectangular. Okay, they hadn't realized that this is the same time within the kind of bounds of experimental uncertainty. So they're not, it's not a much shorter time, it's not a significantly shorter time for this third meter than it is for the second meter. So a mark for saying that basically they are sure about the round and the rectangular one, they're not sure about the square one. Some students are concerned their method does not give conclusive data for the experiment. Suggest why. So this is about what they've done and why it is that it can't really be conclusive. So let's think about how they've actually done that. They've used a stopwatch, okay? That makes it very difficult to time accurately because of reaction time. And here's where I'd like to really, that understanding of the word accurate, okay, is linked to a method. So what are they doing and why does that make it less accurate? And secondly, well, it's not easy really to see exactly when the parachute hits the ground or goes past a meter. Okay, so that it would be my second one. Okay, it's not easy to tell when the parachute was starting the first meter, starting the second meter, etc. Okay, so both these things are linked to the method. It's not easy to time accurately because of human reaction time. Don't just say because of human error. We want to know that in GCSE. We want to know it's about reaction time. Stopwatches are not the most accurate way to measure time because of human reaction time. And really you need this. It's difficult to tell exactly when the parachute passes each point. Okay. Yeah, that's now a hard one because it's evaluative, and this is even harder. How can you improve the practical to increase the accuracy? So again, this is how, so explain how to improve the accuracy of the data. Now if you want to improve accuracy, you've got to think of a different way of conducting it, a change to the method. Here's where again that word accuracy is about changing the method. So you could drop it from a taller height. It would be easier to spot heights if they're taller. Okay, it decreases your percentage uncertainty if you increase the size of the things you're trying to measure. And nextly, the way that I would have done this practical is I'd do a bit of video analysis. Okay, or you could say slow-mo playback, or frame by frame playback is the way they like to term it to measure time. If you've not had a go at that at all by now in year 11, then do have a go at doing something with a bit of video analysis. You can just do it on your smartphone, take a little video, use it to work out the exact times when things happen. You get good motion trends, you get good motion curves. Anyway, moving on. The rectangular parachute hits the ground at 0.47 meters per second. Calculate the change in momentum when the rectangular parachute hits the ground. Now again, you do need to memorize that formula, but they've given you this, so they're not giving you a mark for just knowing the formula. They're telling you which one to use. Now, so really the skill is only in terms of identifying the velocity and identifying that they want the units in kilograms meters per second. So the mass, it's on the previous page, 100 grams. Okay, so what is that in kilograms? That is 0.1 kilograms. And then you're going to reach for your calculator, because even though that's a very easy question to answer, you're just not wanting to do any more thinking than you have to do in an exam. You just let the computer be the brains. 0.047 kilogram meters per second. So basically you've got a mark for putting them in the right place but having the unit converted, and a mark for the correct answer. Okay, next one, draw a free body diagram. Okay, now I found that most people at GCSE find it hard to understand the purpose of a free body diagram. A free body diagram is just considering the forces on one body. So you don't need to draw the whole thing, you just need to draw the mass. Okay, and we're just thinking about the forces on that one body. So what are the forces involved? Well, each body in the world has weight. Okay, so we can put that on straight away. But it does give us a little bit of extra information. We have to draw the free body diagram for the 100 gram mass with the square parachute, so I don't need to draw the parachute, during the second meter of its fall. Right, so let's go back to the second meter. So what is happening to the square parachute and the second meter? Well, it is still speeding up. So what the situation is when it's still accelerating is that the weight has got to be larger than the air resistance or the drag. Okay, it is acceptable to say gravity, but weight's better. It is acceptable to say drag. That's absolutely fine to call it air resistance or drag. They're both acceptable terms. You can just put W and capital D if you like, because that's the terms that we normally use. You get a mark for having the labels basically and the right directions of the arrow. Okay, weight and air resistance. And you get a mark for the air resistance being less than the weight, because when it is still accelerating, the weight is greater than the drag. Thank you very much for watching. There's one more thing I want to say about this actually. There's a lot of people who did this right in the mock exams that my class sat, but they didn't get the point that the square parachute is still speeding up. So I think there's a clue in there that actually you needed to be talking about the square parachute still speeding up because of this question here.
Masters, and this is Gorilla Physics, and we're all about you understanding your physics more so that you're going to enjoy it more, get more confident, and then do better in your exams.